When dealing with lines, we know that the rate of change is given by the slope. Also, the slope of any line is constant, which means that a line's rate of change is constant. If we look at a graph of a nonlinear function, that is, one that's not a straight line, it's clear that the rate of change is not constant. As we can see by this graph here, it's not a straight line, and we can see that the rate of change changes based on where we are on the function. In fact, a slope that isn't constant is what defines nonlinear functions. Because the rate of change isn't constant, we need a more sophisticated concept than slope to describe how fast the curve is changing, the derivative. Before defining what a derivative is, let's take another look at the graph. Suppose we wanted to find the average rate of change between 2 points on the curve, A and B. Well, between these 2 points, y increases by the difference in the y values, which is just y1 minus y0, which we can also call delta y, which just means the change in y. And x increases by x1 minus x0, or delta x. So the average rate of change is simply delta y over delta x, which is y1 minus y0 over x1 minus x0. Notice that this is really just a straight line between the 2 points. This is how we calculate the average rate of change. And so if we rewrite y1 as y0 plus the increase in y, that is delta y. So we're just rewriting the value y1, which is the y value for the second point, as y0, which is the y value for the first point, plus the additional increase in y, delta y, then the average rate of change becomes y0 plus delta y, which again is y1, minus y0 over delta x. So we're just rewriting this average rate of change that we had from the previous slide. If we use functional notation, this becomes f of x0 plus delta x, because functional notation f of x0 is just y0, and f of delta x is delta y, so f of x0 plus delta x is just y0 plus delta y, minus f of x0, because again, f of x0 is y0, and that's all over delta x. But how does the average rate of change between these 2 points help us find the rate of change for the entire curve? Well, suppose we moved x1 closer to x0, decreasing delta x. If we were to continue to do this until delta x becomes very small, the graph of points A and B would look like the following. So here we see point B has moved much closer to A, decreasing that delta x, decreasing the additional change in the x value between the 2 points. The dotted line segment, which still represents the average rate of change between the 2 points, comes closer and closer to being the line that is tangent to the curve at point A. The slope of this line segment then converges to the slope of the tangent at point A as delta x approaches 0. So as delta x gets smaller and smaller, the average rate of change between these 2 points really becomes the tangent line to the curve at the first point, at point A. This is what the derivative is. It's the best approximation of the rate of change of the curve at a single point. The formal definition, denoted dy dx, is the limit as delta x approaches 0, so as the change in x becomes really, really small, of the average rate of change between the 2 points, which is what we already defined. F of x0 plus delta x minus f of x0 divided by delta x. And that just summarizes what we were just talking about. As that delta x gets smaller and smaller, we can estimate how fast the curve is changing by looking at the slope of the tangent. In essence, the derivative tells us how fast a function changes with small changes in x at a specific point on the function. That's the key part. This means that, unlike slope, the derivative will change based on where it is being taken, such as in the following graph. And so here we see the 2 tangent lines at 2 different points on the curve, which represent the derivative at those 2 different points. And we can see it's clear that the slope of those 2 tangent points, those 2 tangent lines, are different, and that's just because the derivative changes based on where you're taking it. And that's at the end of this review.